In this lecture, let us find out the impulse response and step response of a digital system. Okay, so the definition is very simple. You have a digital system and the input is an impulse function. Okay, so you apply del of n to this system. So input is del of n, and whatever the output is, we will denote it by a symbol h of n. Okay, and this h of n is called the impulse response of the system. And this one is input, and this is my output. Okay, if h of n is equal to 0 for n less than 0, then the system will be causal. Okay, it's very easy to say why it is causal, because del of n comes at n is equal to 0, right? Therefore, if the system has an output before n is equal to 0, it means the system is non-causal. See, del of n has the non-zero value only at when n equals 0. So prior to n equals 0, there is no non-zero value. So the input is applied only when n is equal to 0, right? So this is my del of n. So in case my system produces some non-zero value before n is equal to 0, that means the system is non-causal. Therefore, this is the condition for causal system. Similarly, for the same digital system, you take it one more time. Now in this time, instead of applying del of n, now your input is u of n. Okay, for the same digital system, you apply u of n, and the output is usually denoted by small s of n. And the small s of n, the symbol small s is reserved for the analog complex frequency generally, and when there is a chance of confusion, we will not use this s of n to denote unit step response, but generally we will use s of n to denote the unit step response. Okay, so generally later on we will study that when we talk about a bilinear transformation, which is a technique to transfer an analog filter to digital filter or vice versa, we will use some other symbol. Okay, so long as we do not come to the bridge, we will not cross that. We will keep s of n as the unit step response. Unit step response of the digital system. Okay, so we will keep s of n as the unit step response. Now let us take some examples. Okay, so let us pay more attention, because some of these examples are a little tricky, although they look very simple. So example 1, accumulator. So we have seen different types of accumulator, right? So we'll take one by one. Okay, so the first example that we take is that of an accumulator. An accumulator can be of various types. So let us say my accumulator is like this: summation of x of L, where L is going from minus infinity to n. It is an accumulator, and it accumulates data, right? So what do you think its h of n will be? H of n. So h of n means we will have to substitute this x of L by delta L, right? So you have a system. Let's say this is my accumulator, and if the input is x of n and the output is y of n, this y of n is summation of x of L going from minus infinity to n. That's it. This is my accumulator. Now what we are trying to understand is, instead of applying a general signal x of n, I am going to apply delta n for the same system, for the same accumulator. Now what will happen? So you apply this same accumulator, so you will get, now instead of h of n, we said it is going to be, instead of y of n, it is going to be h of n. Now substitute here, instead of x of L, it is del of L going from minus infinity to n. Now if you expand this summation, what will you get? You will get del of minus infinity plus dot 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 del of minus 2 plus del of minus 1 del of 0 plus del of 1, right? It keep on goes up to del of L. Now look at this sequence. This guy is 0, this guy is 0, this also 0, and this is 1. And what about this? This also 0 and this also 0. All are 0 except del of 0, because del of 0 is 1, right? That's what the definition of del of n. Therefore your h of n is equal to 1 only when n is 0, say up to, one second, say up to this point your h of n is 0, right? Afterwards it is 1. Then let me write down properly one more step, because it will confuse you a lot. Okay, see, this index is n and here also the upper limit is n, right? So if I write like this, h of minus 2, what is h of minus 2? Summation of L is equal to minus infinity to minus 2 del of L. Now if you expand the summation, what will you get? You will get del of minus infinity plus dot 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 del of minus 3 plus del of minus 2. All are 0. Therefore h of minus 2 is equal to 0. Similarly, you can say h of minus 3 is 0, h of minus 4 is 0, all are 0 up to, you can write down up to h of minus infinity is 0. So this is one set of values we got now. And then now let me find out h of minus 1. What will happen now? Same summation. L is equal to minus infinity to minus 1 del of L. Expand the summation. Del of minus infinity plus dot 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 del of minus 2. You stop at del of minus 1. Now again all are vanishing, so it is 0. So h of minus 1 also 0, right? Now let us try to find out h of 0. Then what will happen? Your summation will be L is equal to minus infinity to 0, then del of L, right? So this is going to be again del of minus infinity plus dot 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 del of minus 2 plus del of minus 1 plus del of 0. So this guy vanishes, this guy will disappear, and this also will be 0, and this is going to be 1 now. Now h of 0 is equal to 1. Now let us try to find out h of 1 plus 1. Sigma L is going from minus infinity to 1 del of L. Okay. Then expand the summation. It is going to be del of minus infinity plus dot 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 del of minus 2 plus del of minus 1 del of 0 plus del of 1 plus, no, I'm sorry, you must stop here. That's it. Now look at the beauty. This is 0, this is 0, and this also 0, but this is non-zero. It is equal to 1, and again this is 0. Now h of 1 also 1. H of 0 is 1. H of 1 also will be equal to 1. Therefore, by the same way, if you find out h of 2, then this also will be 1. h of 3 will be 1. So we got set of values. So h of minus infinity 0, h of minus 2 0, h of minus 1 is equal to 0, h of 0 is equal to 1, h of 1 is equal to 1, h of 2 is equal to 1. Then now don't you see that this is the exactly matches with the unit step signal, right? If you plot it, 0, at 0 you have 1, at minus 1 0, minus 2 0, minus 3 0, right? At 1 it is 1, at 2 it is 1, at 3 also it is 1. Then what is this? This is my unit step signal. Therefore you take a accumulator, and if the input is del of n and my output is h of n, this h of n is simply 1 when n is greater than or equal to 0 and 0 otherwise. So this is my impulse response of an accumulator. So in this way we can find the impulse response of a system, given system. So therefore h of n is equal to u of n. If n is less than 0, then del of n is a negative number. So negative number is identically equal to 0. Therefore h of n is 0 for n less than 0. Okay, h of n is 0 for negative values of n. Okay, now don't you see that this is the exactly definition of, or precisely the definition of unit step function? So therefore h of n is equal to u of n. Okay, now let us take another version of accumulator. Suppose if I describe my accumulator in the following way: k is equal to 0 to infinity x of n minus k. This is also one way of describing an accumulator. Okay, so in other words, it accumulates data from n is equal to 0 up to infinity. Okay, that's all the range of n. So now the question is, what would be its h of n? Okay, so you have a system accumulator and the input is del of wait a minute, x of n, the output is y of n. What is output? Summation of, it accumulates 0 onwards, x of n minus k. Now instead of applying x of n, what you do? You apply del of n to the same accumulator. Same accumulator. And now instead of calling y of n, let us call it h of n. So now limit does not change. Instead of x, you put a del of n minus k. That's it. Now what is this? Don't you see that this is precisely equal to u of n? You can verify it. Okay, so now expand this. If you expand this, let us substitute k, n is equal to 0 in this expression. N is equal to 0. What will happen? H of 0 is equal to del of let me write down properly. K is equal to 0 to infinity, then del of n minus k. N you substitute 0 minus k. Now this is going to be del of 0 minus k, again del of minus k, right? This is k is equal to 0 to infinity, del of minus k. Substitute k equals to 0. So 0, then k is equal to 1, then del of minus 1 plus del of minus 2, and so on and so forth. This is 0, this is 0, and this is non-zero, which is equal to 1. Therefore h of 0 is equal to 1. Similarly, you can find out h of 1. So how will you find out h of 1? H of 1 is equal to, again, the limit does not change, okay? K is equal to 0 to infinity. So instead of del of n minus k, you substitute 1 minus k. Now expand the summation. Substitute k is equal to 0, you'll get del of 1, right? Substitute k is equal to 1, then you'll get del of 0. Substitute k is equal to 2, you'll get del of minus 1 plus and so on and so forth. This is 0, this is 0 identically equal to 0, and this is 1, therefore 1. So h of 1 is also 1. Similarly, you can find that h of 2 is equal to 1 and h of 3 is equal to 1 and so on and so forth. But if you try to find out h of minus 1, then it will be 0, h of minus, by the same way you can find out. Okay, for example, h of minus 1, which is summation of k is equal to 0 to infinity, del of n minus k, right? Del of, instead of n, I have minus 1 minus k. Now expand the summation. Substitute k is equal to 0, you'll get del of minus 1. Substitute k is equal to 1, you'll get del of k is equal to 1, you'll get 0, right? 0. Substitute k is equal to, what am I doing? No. You'll get, I'm sorry. Substitute k is equal to 1, then 1 minus 1, it becomes minus 2 plus. Substitute k is equal to k is equal to 2, then minus 1 minus 2, it is del of minus 3, and so on and so forth. So all are 0. Therefore h of minus 1 is equal to 0, h of minus 2 is equal to 0, h of minus 3 is equal to 0, but h of 0 is equal to 1, h of 1 is equal to 1, h of 2 is equal to 1. So now don't you see that this is precisely the definition of our unit step function? So therefore in this case also h of n is equal to u of n, that's all. So although the definitions of the two accumulators are different, the impulse response is the same. Okay, now let us take the third description of the accumulator in terms of initial condition. See, in one of the previous lectures I explained the different way of describing the accumulator. Now the same accumulator can be described in this following manner, like y of n is equal to y of minus 1 summation of, let's say L is equal to 0 to n x of L. Now what do you think its impulse response will be? Okay, so you substitute, instead of x of L, you substitute del of L. Okay, if the input is x of n, output is y of n for the accumulator. Okay, what is y of n? Y of n is equal to y of minus 1 plus summation of L is equal to 0 to n x of L. Now you take the same system, same accumulator. Instead of x of n, you apply del of n. Now instead of calling y of n, we will call it h of n. H of n is equal to, this y becomes h of minus 1 plus sigma L is equal to 0 to n. Instead of x of L, it becomes del of L. Now expand this, del of L, then L is equal to 0, 1, 2, 3, then this is always equal to 1. Therefore, irrespective of the n value, therefore h of n is equal to h of minus 1, only for n greater than 0, okay, not for less than 0. If you substitute n less than 0, then it will be something different. We will see that, no problem. Let us take two cases in this. For example, if say n is less than 0, in case let us take n is equal to minus 1, then what is going to happen in this expression? H of minus 1 is equal to, no, I am sorry. In this summation I cannot take negative values, right? Because the running variable runs from 0 to n, that means only positive values. So this expression is valid for non-negative values of n, that is n must be greater than or 0. If n less than 0, then this guy will go away and this will come. Okay, so therefore, I'm sorry. Okay, because look at the index here. The index is only for positive values of n, right? L is equal to 0 to n. It is not taking negative values. Therefore, I need to consider positive values, positive value for n. So in that case, if it is negative, then this whole thing will disappear for n less than 0. Therefore, h of n is equal to h of minus 1 for n less than 0, and h of n is equal to this expression. So if you expand that, maybe I'll work out here. Let's say n is equal to 1, then h of 1 is equal to h of minus 1 plus summation of L is equal to 0 to 1 del of L. Expand this, h of minus 1 plus del of 0 plus del of 1. Anyway, this is 0, del of 1 is 1. Therefore, h of minus 1 plus 1. What is this? H of plus 1. Similarly, you can find out h of 0. H of 0 equal to, in this expression, h of minus 1 in the summation L is equal to 0. The upper limit also 0, right? So del of L. Now expand this, h of minus 1 plus del of 0 alone. Anyway, this del of 0 is 1. Therefore, h of 0 also h of minus 1 plus 1. Similarly, you can find out h of 2. H of 2 also will also be h of minus 1 plus 1. Like this, it keep on goes. So in general, h of n can be written as h of minus 1 plus 1 for n is greater than or equal to 0. Okay, now if you look at this, this is a non-linear system. Okay, this accumulator, sorry, this expression. This is the non-linear system that we have already proved in the last lecture. So non-linear systems can also have an impulse responses. Okay, but the other property that we are going to discuss will not hold. Convolution, for example, will not hold for a non-linear system in the form that we are going to present it. Okay, so it doesn't mean that non-linear system does not have the impulse response. So non-linear systems will also have an impulse response, but the other properties like convolution and all will not hold. Okay, let me take one more example. Upsampler. This we already discussed. What is what the upsampler is? Okay, so the upsampler, as you know, is described by y of n is equal to x of n by L for n is equal to 0 plus or minus L plus or minus 2L and so on and so forth, and 0 otherwise. Now the question is, what is the impulse response? Now by the same way we can find out the impulse response of an upsampler. So how do you denote the upsampler? You put an upside arrow mark, and the sampling rate you can put here, and if the input is x of n and the output is y of n, this y of n is x of n by L. Now you take the same system, upsampler. Now instead of x of n, you apply del of n. Now instead of calling y of n, you call it h of n. H of n is equal to del of n by L. Now we know that this del of n by L exists only for n is equal to 0 and n is equal to plus or minus L, right? Because this index should be integer. Okay, index cannot be non-integer, right? So index should be integer. So when will it be integer? When n is equal to 0, then n is equal to L or minus L, n is equal to 2L or minus 2L, n is equal to 3L or minus 3L, and so on and so forth. Now if you substitute n is equal to L, then what is going to happen? N is equal to 0, then h of 0 is equal to del of 0, you will get 1, no problem, right? Now this is the value for n is equal to 0. Now you substitute n is equal to 1, then h of 1 is del of 1 by L. Okay, again I don't know how this will be based on the L value, so it does not again the index cannot be a rational number. Okay, it cannot be a real number, it should be an integer. So now let me take n is equal to L. So h of L is equal to del of L by L. Del of L by L is going to be 1. By definition, this del of 1 is going to be 0. Similarly, you substitute n is equal to minus L. Then again h of minus L is equal to del of minus L by plus L, which is del of minus 1. So this is again 0. You substitute n is equal to 2L, then h of 2L is equal to del of 2L by L, that is del of 2. Again this is 0. Like that you can substitute various values. Only one case will not vanish, that is n is equal to 0. Therefore h of n is equal to 1 for n is equal to 0 and 0 otherwise. Okay, now don't you see that this is the definition of delta of n? So h of n is equal to delta of n. That means what? The input is an impulse function and the output is also an impulse function. Therefore h of n simply equal to del of n. Suppose we want to find out a unit step response s of t. What do you think s of t would be for this case? See, I have an upsampler. The input is x of n, y of n is equal to x of n by L. This is my upsampler. Now what we are asked is, instead of del of n, I am giving an input u of n. Now this y of n becomes not h of n, because the input is unit step signal. Let me call it s of n, small s of n. So in this case, u of this x of n is replaced by u of n by L. Okay, now we know the definition of u of n, and this index should be, argument should be an integer. Therefore when will it be an integer? When n is equal to 0, when n is equal to plus L, minus L, plus 2L, minus 2L, and so on so forth. And I'm sorry, not for this guy. Okay, not for this guy, because that won't take the negative value, right? So it takes only plus L, plus 2L, plus 3L, plus 4L, and so on so forth. Negative values it will not take, because when the argument is negative for an unit step function, then it will be 0. Therefore h of 0 is equal to u of 0, which is 1. H of L is equal to u of 1, this is also 1. H of 2L is equal to u of 2L by L, right? 2L by L, L and L will get cancelled. Then it is u of 2 is 1. If you substitute h of minus L, then what will happen? U of minus L divided by L, u of minus 1 is 0. Similarly, h of minus 2L then u of minus 2l divided by l and l will get cancelled. So u of minus 2, then this is also 0. Therefore, what is your h of 0? H of n. H of n is 1. Let me write down in this way. 1. H of n is equal to 1. If n is equal to 0, L, 2L, 3L and so on and so forth, and 0 otherwise. Okay, now the question is, can we write it in the compact form? Okay, that is the next question. So how do we write this? Okay, see, if you look at here you substituted n is equal to 0, and here n is equal to L, n is equal to 2L and so on and so forth, right? So at this point the output is 1, the value is 1, and here also 1. So at n is equal to 0, the value is 1, at L the value is 1, at 2L the value is 1, at 3L the value is 1. Now this I can write as del of n. How can I write this guy in terms of impulse function? I can write del of n minus L, right? And this one I can write it as del of n minus 2L, and this guy I can write it in terms of del of n minus 3L and so on and so forth. So therefore in compact form I can write as del of n plus del of n minus L plus del of n minus 2L plus del of n minus 3L and so on and so forth. So let me write it in the form of summation, compact notation. So therefore del of n minus KL, where k is equal to 0 to infinity, this is my h of n. Okay, so is it a step response? This is step response, right? Then why did I put h of n here? I'm really sorry. Okay, this all are s of n. Okay, I'm very sorry. Here also. Sorry for about that. S of 0, S of L, S of 2L, S of minus 2L, and this is S of n. Then this is S of n, S of n. That's it. Because most of the time, generally we discuss impulse response. That's why my mind is always thinking about impulse response instead of thinking about step response. Okay, now see, the upsampler is a time varying system, right? So although the upsampler is a time varying system, it has an impulse response. That means the time varying system also do have an impulse response. Okay, but it is a linear system. But it is a linear system. Okay, so the upsampler is a linear system, but it's still but it is a time varying system, linear time varying system, and it has an impulse response. Similarly, you can find the impulse response and step response for downsampler also. Okay, take the downsampler equation system and then you can find out. Now the next one we will consider interpolator. A simplest interpolator is something like this. It takes the nth sample value, let's say n, and half of the next sample, okay, half of the immediate future value, okay. Let's say this is my present value. At present I am talking about n, and the immediate future is n plus 1. Immediate future value, this one is, and then you take immediate past value, so this is n minus 1. So what this interpolator will do is it takes x of n, okay, it adds with half of the immediate future value, that is x of n plus 1 divided by 2, and also it takes half of the immediate past value, this is immediate past value, x of n minus 1 by 2. Okay, so this is the interpolator. Okay, so interpolator is nothing but it does this job. The input is x of n and the output is y of n. This y of n is x of n present value plus half of the immediate past, x of n minus 1, plus half of the immediate future, x of n plus 1. This is the interpolator. And by looking at, you can say this is a non-causal system, right? Obviously this is a non-causal system because the present output y of n depends on the future input x of n plus 1. Therefore it is a non-causal system. So the interpolator is a non-causal system. Now the question is, what would be its impulse response? H of n. So how will you find out? Okay, for the same interpolator, you apply del of n and the output is now, so instead of y of n, it is going to be h of n. Now this h of n is equal to del of n, right, plus 1 half del of n minus 1 plus del of n plus 1. Anyway, this del of n minus 1 and del of n plus 1 would be 0. I'm sorry, it's not 0. I'm sorry, it is not 0. Okay, based on the n value only it changes. So this is my h of n. If you plot it, then how does it look? At n is equal to 0, the value is 1. This is my del of n. What is del of n minus 1 here? But its strength is scaled by half. Therefore, half of the value, 1 half at n is equal to 1. This is half times del of n minus 1. One second. Let me write. This is not 0. Let me write del of n. Okay. It is at n. And this one is n minus 1th sample. Here its value is half. And this, how do you describe mathematically? 1 half times del of n minus 1. That's it. So this is the interpolator. Okay. Now it is interesting to find out its unit step response. Okay, let us find out. Same, you take the same interpolator. Now instead of del of n, I am going to apply u of n And now by this time, instead of calling h of n, we are going to call it s of n. Now here del of n, you put a u of n plus 1 half of u of n minus 1 plus u of n plus 1. Okay, now my step response is going to be summation of 3 signals. What are these 3 signals? One is unit step response, unit step signal like this, 0 1 2 3. This is my u of n. Now u of n minus 1, n minus 1 means it is a delayed version of u of n by 1 sample. Okay, it has non-zero value here, but by this now the strength is half. Now here the value is 0, and here it is off, here also it is off, and here also it is half. 1 half, 1 half, 1 half. What is this? This is 1 by 2 u of n minus 1. Now the next one is, it starts at minus 1 actually. 1 half, 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 like that. Okay, this is 1 by 2 u of n plus 1. Now add all these 3 guys, add them up. Then at minus 1 you have 1 half. At 0, here half, and here 1 plus half, 1 and half, 1.5. And here at n is equal to 1, you have 1, here half, and here half, and here 1. So 1 plus half, it is 2. And here also it is 2. At 2 it is 2, at 3 it is 2, at 4 it is 2, and so on and so forth. Okay, so it remains 2 forever after n is equal to 0. Okay, therefore your step response s of n is equal to 1 by 2 for n is equal to minus 1, 1.5 for n is equal to 0, and 2, n is equal to 3 onwards. Am I correct? I am very sorry. 1.5 at 0, and 2 on 1 onwards, plus 1 onwards, it remains 2 forever, and 0 otherwise, or negative values of time. That's it. Okay, so this is how one computes the unit step response. Okay, and one can compute step response, unit step response, and impulse response also. Okay, so anyway, in this course we will not bring non-linear systems or time varying systems. Okay, we will mostly generally dealing with the linear time invariant systems. Okay, so we will be interested in only linear time invariant systems, LTI systems. So we will talk about purely LTI systems in this course. We will not get into non-linear systems or time varying systems. So in the next lecture I'll start with the LTI systems. Okay, so let me stop at this point. Thank you very much.